So the last section here is about interpreting regressions in a causal way. This is by far the most interesting, I think, and also the thing that people most want to be doing and do implicitly, even though they say, oh, this is just an association, it's just descriptive. Implicitly, they think it's causal. But it helps to understand what are the assumptions that you need to make in order to actually ascribe that causal interpretation, because then you can critique how far off you think this actually might be. So let's go back to our identification lecture where we saw that to estimate a causal effect, it's usually the difference or the ratio of these expected values of the potential outcomes. And to estimate the expected value of a potential outcome, which we can never observe for everybody, we saw that it suffices to estimate the expected value of this conditional mean function if we kind of plug everyone in. And essentially this is asking, okay, if this person were treated according to value A as opposed to whatever they were actually treated at, what would have the outcome been? We collect all those values, we take the average. And of course, we can't take the population average, so we have to take a sample average. So this is our estimator. And then we also don't know this true conditional means function, so we have to estimate it. But now we have tools to do that, right? Now we have regression. And so let's see how we can do that. Let's check it out in R. What does that process look like? So I've written the code already because there's a lot, but I'll walk you through it. Okay, so first off, let's just set up a data generating process. Again, in the reality, you don't have this, but I'm just showing you here so that we have something to compare to in terms of truth, so that you can see that the regression is actually doing better than we could if we didn't do it. So here, let's say this is our data generating process. This is a causal data generating process, so we have y0 and y1, and we also have the observed value y, and the true conditional mean of y given a and x is given by this function up here, by construction. Okay, so if I take a really large sample and I can compute the true value of the average treatment effect, and it's actually 2 exactly. If I could do this analytically, but here I'm just getting an approximation by getting a really large sample and taking the mean of y1 minus the mean of y0. And now let's sample some data. And in the observed data, we don't have a population, we just have some small sample, and we also don't get to observe y1 and y0, we just observe y, the observed outcome. And we can, of course, do the naive ATE estimate. We've already seen that. That's where we take the subsample of people who had treated minus an average y, and then take the subsample of people who were not treated, take the average of y, and take the difference. And here we see that the answer we get, that we see that the effect of treatment here is 3, when really we know it's 2, okay? In reality, we couldn't know it's 2, but if we had done this, we would have gotten the wrong answer, basically. Now, let me show you what happens if I estimate this based on the true conditional mean function, because here I know mu, okay? Because I wrote it up there, so I know what that is. In reality, I couldn't know that, but here I do know it, so let me just show you that this works. This is 2. So what am I implementing here? This is this, right? So I'm taking the sample average. This is just in our observed data, but I'm asking here, what would happen to every person in the observed data if I forced their treatment to be 1? And what would happen to every person in the observed data on average if I forced their treatment to be 0? And here I get the right answer. But of course, the problem is we don't actually know what this is, so we can't do this. This is something we couldn't do in practice, but I'm showing you that it works, okay? What can we do in practice, finally? Well, we have linear regression. So we can fit a linear regression model, okay? We have that, okay? And now, with that linear regression, what are we gonna do? Let's use it to predict the outcomes of these people had they been treated and had they not been treated. So the way I'm gonna do that is I'm gonna use the predict function with linear regression, but instead of passing it the observed data, I'm gonna pass it the observed data, and then I'm gonna force the treatment in that observed data to be 1, okay? So I'm creating a copy of the data set where everyone was treated. And then here I'm making a copy of the data set where nobody was treated. And I'm asking this to create the prediction of the outcome for those 2 fake data sets, okay? So it's mu hat 1 and mu hat 0. right? So these are my predictions for each 100 people, assuming they had been treated. And these are my predictions for all those 100 people, assuming they had not been treated. And now what I do is I just average those, and I take the difference. And I get basically the right answer, okay? So that's great. Okay, regression has saved us here from this confounding due to x, because if we had been doing this naive ATE estimate, we would have gotten something much worse, and that's the only thing we've been able to do until now. So this gives us a much better estimate of the true causal effect. And we can make some plots to. Sorry, this is just to make the plots look pretty. Okay, so I can make some plots. So these are the data that I'm looking at here. These are my treated people and my untreated, and you can see what's going on is that I have more of the people who are low values of x. So you can think of this as like age or something. The people who are having low values of x are also typically not treated, and the people who have high values of x are typically treated. And so when I look at the means of y in those two subgroups, right? They're going to be pretty far apart because here I'm not taking into account all the people that should be here. If I actually treated all of these people would kind of be over here. But the group mean of these guys is not taking into account all those people that are missing, and so it's going to be high. And similarly here, this group mean isn't going to take account all the missing values that are in here, so it's going to be artificially low, and that's why we get an ATE of like 3 when it should be 2. So what happens if here I'm plotting the true conditional mean functions that I know, all right? But in reality, I do not get to see those. What I get to see are just the data. But here I can plot, these are the linear regression fits of those conditional means. So you can see they're pretty close in this case. And now, lastly, what I'm putting on here, these little empty dots, are the predictions for everybody. So each of these empty dots corresponds to either a full gray dot or a full pink dot. So you can see here I'm getting these empty dots, which are predictions for all of these pink people who got treated. It's their predictions for what would have happened to them if they weren't treated. Okay, and then vice versa, all of these dots are standing in as the predictions for what these guys would have happened to them if they were treated, contrary to the fact that they actually were not, right? But now we've basically filled in all of the missing data with these predictions, and we can average all of these gray dots, the empty ones, and all of these pink dots, the empty ones, and take the difference of those two averages. And that is a pretty good estimate of our causal average treatment effect. All right, so that's great. Linear regression is effective in that sense. I'm going to show you one cute little thing about the ATE. So what we were doing is this. So we're taking the sample average of my predictions for forcing everyone to be treated. So again, think of this as like a mutate, where I take my data set and I force my A to be 1. So I create a copy of the data set where all the A's are 1s, and then I put that through the prediction function. Similarly here, I force all the A's to be 0s, I put that to the prediction function. So these are the difference of the two predictions. So if I actually write out what that is for a simple linear regression model where I have coefficient on treatment and a coefficient on x, what's a single variable x, I get something like this. So we know mu hat of this, I'm just going to plug in this 1 for wherever the a goes. So the a is usually multiplied by the coefficient on a, and the x is multiplied by the coefficient on x. So here since I'm forcing the a to be 1, I'm just going to get a 1 here. And since this one I'm forcing it to be 0, it's going to be a 0. If I take the difference, the beta 1s cancel, the x beta x's cancel, and what we're left with is just this 1 times beta a, and that's just beta hat a, okay? Because I'm going to have, if I add up n of these and I divide by n, that the sum goes away. And so I'm just left with this. So what this tells you is that for a simple regression model, you can just look at the coefficient on treatment, and that is going to be the estimate of the ATE. But this is just a special case. And by the way, you can see that in this example, if I look at, what did I call the thing? Lin reg? Okay. So if I look at lin reg, you see that my coefficient on A, this is indeed the ATE estimate that we got when we took this difference here, 2.03 2.03, same thing. So I'm showing you that that in this special case, you can just look at that coefficient. But this is just a special case, okay? So in most cases, that coefficient is totally meaningless. Okay, I have this meme here because people are just taught to look at the coefficient, and they learn this simple case, and then they think, oh, that always works. I can always just look at the coefficient. But no, okay, you focus on the S-span. What are you trying to estimate? Okay, it's the ATE. It's defined with these potential outcomes. You use regression, you impute the two potential outcomes, you take the mean of the two differences of the potential outcomes, and then that's your ATE. That's the definition of the ATE. It all makes sense. It's from the plugin kind of philosophy. You just don't know the true regression, so you use this prediction model instead. All good, right? Oh no, yeah, just read the causal effect off the regression table. It's just this coefficient. But that is, it's typically not the case. And we'll get into cases where it's not. But for example, if you have an interaction term, and that's discussed in a different part of the lecture. But let's say you have a coefficient on the product of A and X, or you have some other stuff going on with there's nonlinearities. Then this coefficient by itself is not meaningful, and you have to look at whatever difference. I mean, you can work it out mathematically if you want. It's always going to be some function of the different coefficients, but the easiest way is to just take the difference of the predictions. It's so simple. So why are people just always trying to look at these coefficients? It's crazy. Okay, so let's do this with the insurance data set. Let's use linear regression to estimate the causal effect of smoking on total charges and include everything else as covariates. Let's go get this. Okay, so we have our data. So the first step is to fit our linear model. Oh, just include everything. Okay, so use a little dot to just include everything. So we have that. So now we need to ask what would have happened to these people? What would have their charges been had they been all smokers, contrary to the fact? So it's the effect of smoking. So I think that variable is called smoker. Yeah. Okay. So to do that, I will predict using that model on the insurance data, but I'm going to say that everyone was a smoker. Okay. Smoker is not a oh, okay. So let me first so I think the issue here is that let me just see. Okay, so yeah, smoker is coded as yes or no. So when I do this here, instead of setting it equal to 1, I have to set it equal to yes. I think that should do it. Okay, great. So now those are my predictions. You can fix this, what I was trying to do up here actually, which I will admit, but you can also fix this by just changing your original data so that everything is coded consistently as 0, 1, or however you want it. And then it just has to be consistent when you do the prediction step. Okay, so now let's do the predictions, again, contrary to the fact, if everyone had not been smokers. And now we'll just take that mean minus this mean. Great. So this is the effect. So if you're a smoker, your charges, that increases your charges according to this analysis and some assumptions that we're going to discuss in a second. The causal effect of smoking is to increase. If we took the whole population and we made them smokers versus if we didn't make them all smokers, the charges would increase on average by like $23,000. So that's very interesting. Now the question here is, what are the causal assumptions required to believe that this thing represents a causal ATE? So we've said that, okay, to get from this point to this point, we can do linear regression, right? So that we're estimating this function. Cool, let's say we can do that well. We still have to make causal assumptions to go from here to here, right? And those causal assumptions were discussed in the last lecture, but just to remind you, we need essentially there to be no unobserved confounding. So that's the big one. No unobserved confounding. So if we look at this, right, we have to say, okay, there has to be nothing else in the world that could affect whether somebody's a smoker, and also what their insurance charges are that is not measured in here. But that's clearly ridiculous, right? Here, there's a whole bunch of other stuff that is not measured. For example, socioeconomic status doesn't seem to be indicated anywhere. Maybe you could kind of, glean a little bit about what that is based on the region, but this is a very big kind of quadrant region, how many children they have, BMI. So these things could be capturing some of those effects, but not really, right? So clearly that is a huge confounder that is missing. And so is this the causal ATE? Probably not, right? There's probably some amount of bias that is not being accounted for because we're missing that very important confounder. But by understanding these assumptions, now we know, how to think about the problem, right? And we can think about, okay, if I were to include that confounder, how do we think that this might change? And so it still helps, right, to understand what's going on, even though we don't actually have something that is a perfectly representative of the causal AT. And now the last question here: how can or should you interpret the other coefficients? So here I did the kind of plug-in estimation, right? Another really nice thing about the plug-in estimator, by the way, when you do it this way, is that you don't get the other coefficients. You don't even see them. And that's a good thing because they don't matter. They're completely irrelevant. If what you care about is the causal effect of smoking on insurance, why are you going to go and do something like this and write about all this other stuff in your paper? Okay, it literally does not matter, because you can start. Then if you're going to start looking at this coefficient, right? Oh, okay. So having children increases the okay. So let's say, okay, this thing we know is actually going to be this coefficient here, right? So maybe we can look at this, and that's not always the case. In this case, it is, but usually, more generally, it's not. Let's say you go look at this and you try to interpret this the same way as you interpret that, right? Oh, the effect of having more children increases on average charges by some amount. That is very tenuous, because in order to interpret this, we had to think carefully about what are the confounders, right? Is this really representative of a causal ATE? And also, this is a binary variable. This is not. So since this is not a binary variable, the causal interpretation is also a little bit trickier and not necessarily uniquely defined. But you say, okay, if everyone had one more child, this is the population average of how much their insurance costs would go up causally. Well, again, if you want to give it that interpretation, you have to make all the same kinds of assumptions about confounding. Is there an external variable that affects both children and how many children somebody has and the charges? And there again, socioeconomic status would play in. But generally, it's much harder to do for these other covariates. If you design your study carefully and you think about how the data are collected, you're usually paying attention to some kind of time ordering, right? So your other confounders are things that could not possibly have been affected by your exposure, or else including them would give you some bias. We'll talk more about that later. But you just haven't been so careful about these other confounders that you're including, and so it could be that this is a collider, or that your exposure is a mediator on the path from one of the other covariates to your outcome. And then you definitely don't want to interpret this in any kind of causal way. And so, okay, sure, you can interpret it descriptively, but like we already talked about, there's a lot of problems with doing that, and it's also contextual on what else is in the model. So, zooming out, just why do you care? Why do you care? And if you do care about it, then define a question that actually makes sense, and then go answer that question in a way that makes sense for that question. Don't just make a regression table and then say, oh, this regression table can tell me everything that I want to know, and let me just look at these vibes. and then publish a paper that's actually trying to go after a lot of different things with one regression table. If you have a question, you need to think about that question carefully. Okay. So last thing to talk about that here. I showed you an example where this linear regression, it does great. We can estimate the conditional mean very well, and then therefore we get a good estimate of the causal effect. So here's another example of doing that. The code is a little bit different, but it's basically doing the same thing. I'm getting my predictions for everyone, assuming treatment and control, and then averaging the differences. And here I'm repeating, what I'm doing differently is I'm repeating this experiment 1,000 times and showing you that the bias is essentially 0. So if I take the average guess and then I subtract off the true ATE, they're no different. So I'm getting the right answer on average. Now, if I change, however, my true conditional mean function, so in this case, actually, my conditional mean function, the true conditional mean, was given by a linear function. So the value of a, so the coefficient on a is 1 and the coefficient on x is -5. But if I change that and now I add some nonlinear, now x is some nonlinear function, I'm doing the same estimator. It's my same linear regression estimator. Now I'm getting a substantial bias. So the point is that this linear regression estimator is really only as good as how well you're estimating the conditional means. And that makes sense because, let me actually just skip ahead here. This should make sense to you because what you're trying to get at is this, right? This is the true estimand. And if you're telling me that I'm approximating this estimand with this value, but this function is nowhere near this function, and it's actually a really bad guess of that function, then these two things are not going to be the same, right? And if you're telling me not only is it a bad guess, but it's systematically a bad guess, like this function is not even linear, and my guess is always linear, that's going to be bad. So let me show you maybe a little bit more mechanically why that can happen. So here is a case where the conditional means are linear, and here's a case where they're not. And the issue is that the linear function can't correctly extrapolate the nonlinear relationships. So with the empty dots, I'm showing the potential outcomes, the ones that I'm not observing, and the filled ones, I'm showing you the ones that I am observing in both cases. So what happens in this case, if I fit my regression model, I'm doing a pretty good job because it's a line, right? I'm gonna do a good job at guessing what these values are out here, right? This is gonna fit. This linear fit is fitting the observed values well, but it's also fitting the unobserved values well. And same over here. If I fit this with a line, I'm doing well. Now, over here, let's say I fit linear regression, it's gonna fit something like this, okay? And then this one, maybe something like that. And the point is that this is bad, okay? The linear regression, since it's extrapolating in a linear way, it's not capturing the fact that there's actually some curvature here. And therefore, we're not actually fitting, we care about how well we fit the observed data, but what we want is to fit this kind of like a unobserved data over here. But since we're constraining ourselves to just fitting lines, it's not able to do something like that, okay? And if it were, then we would do well. But since it's not, we're getting this fit here. And if you look at the this kind of difference here, which is the ATE, it's smaller than it actually should be. The ATE should be the difference between these two curves, which is much bigger. Okay, so we're gonna be underestimating systematically here, and that creates the bias. So this is called model misspecification bias. The true conditional mean is something more complicated, but than what you specified. You misspecified the model. You said it's linear, but really it's not. So you're getting this bias, and it's exactly this issue. Even if you have good identification, you've measured every confounder. You're great. You can theoretically identify it, but then you mess up the estimation. You messed it up because you did linear regression, and really there's some nonlinearity here. Then you're still screwed. You've introduced systematic bias by doing the estimation in a way where it cannot actually capture the relationships in the data. And therefore, even though you measured all of the right things, you're not able to explain the relationship right. And you're not going to do a good job estimating the ATE. There's going to be a systematic bias. So that really sucks, okay? So let's think about this example again, where we have the insurance data set. We've used linear regression to estimate the effect of smoking on total charges. And now we actually already talked about the causal assumptions, right? We need to assume that we've measured all of the relevant confounders. And clearly in this example, we didn't. Clearly there's stuff out there that is confounding the relationship between smoking and total insurance charges. So we already are kind of screwed here, right? Here I put a check mark, but in this example, we don't have a check mark there. But at least we understand how to, maybe what we could do about that and how we would do that better. And perhaps if you're an expert in this domain, you even understand how including that might change the result. So that at least is a starting point. Now we're asking, okay, well, what about this assumption? How are we doing there? What are the statistical assumptions that are required to believe that your estimate represents at least the observable ATE? So is this thing actually an estimate of this quantity, even if this quantity is not an estimate of this, is not the same as this, right? So there's three separate things here. There's this number, there's this number. Those may or may not be the same, depending on whether we've measured all those confounders. And there's this number and this random quantity down here, and we want to know, is this thing kind of unbiased for whatever this number is, whether or not this number is actually equal to the thing we care about. And like we talked about, in this case, the statistical assumptions that are required are basically that we have to rule out any kind of nonlinearities, right? If there is some kind of nonlinearity, the way that we did this analysis, we assumed here that charges is a linear function. The way that we set this up, charges is a linear function of like smoker plus age plus BMI, whatever, so on and so forth. But that's also a kind of ridiculous assumption because, in fact, I can probably just plot this. Let's say just a cheap plot of charges and age, maybe. Is it called scatter? I never use the base R plotting. Maybe it's just plot. Okay, this is, oh, it went the other way. Okay, right. Okay, so you can see here, well, one, there's a lot of variability, right? For any age bucket, there's a lot of variability, and it could be that some of these upper tranches are smokers or people with more children. Whatever is causing that variability. Maybe it's something that we're measuring. Maybe it's something that we're not measuring. But overall, we also see this kind of trend. And the question is this trend linear? And I actually, it's kind of hard to see because of the way that that it's scaled. But I actually think it's not. And maybe if we put it like this. So yeah. So here you can see it's kind of actually curving up a bit, right? And maybe for BMI, we'll see something similar. I don't know. So BMI, this one is more complicated, but yeah, here it looks again like there's maybe two groups. So we're not really seeing the conditional mean conditional on everything. Here we're just looking at kind of like collapsing it down marginally onto BMI. But we're kind of looking at like these different views of the overall conditional mean function, and it seems like there could definitely be some nonlinearity in some subset of the population. Maybe these people up here are the smokers again, right? And then the trend there would be something like this, and that would be a nonlinearity as well. So you can empirically assess whether or not it appears that there are some nonlinearities here, and in this situation, it looks like there probably are, and therefore this estimate here of the ATE, of the observable ATE, is probably biased. And it's biased because of the model misspecification. We're not doing a good job actually specifying what the model needs to be. And so there are kind of two gaps, okay? There are two gaps. One, in this analysis, in this particular analysis, we could be failing here. And the solution to that would be to go collect more data. Not necessarily more people, but more covariates, more confounders that we could adjust for. And that would potentially help us, or design the study a little bit better. And then there's this second error, which is that we're maybe not doing a good job estimating because we're using linear regression here, and we need to do something a bit more sophisticated. And that is going to be discussed. It's discussed in another part of this lecture, and also more later in the course. So that's about assumptions for causal interpretation. So as you can see, the causal interpretation, it's all about what assumptions can you make, right? And understanding what those assumptions are, and especially for the causal assumptions, it requires understanding these conditional dependencies, right? That's why we have to learn all about those conditional independence things. For statistical assumptions, it requires us understanding, what a conditional expectation even is, and how that conditional expectation can actually be a nonlinear function. That's why we had to do all of that stuff. So you see all of the stuff that we were doing, which may have seemed kind of abstract. I'm never going to use this. Yeah, you're never going to use that, but it's all required. If you don't have that, you can't really understand at a fundamental level what are the assumptions you're making and how can you evaluate them vis-a-vis the real world. So I want to give you one kind of cool special case, which is that this problem here, this estimation problem, totally goes away if you have randomized treatment, which is really interesting because when you have randomized treatment, you get identification for free, right? Because there's no confounders. Awesome. So you might think in a randomized trial, I at least have that. But then if I do linear regression, I might still have this problem because even if it's randomized, the conditional mean, the relationship between the outcome and the covariates might not necessarily be linear. And so if I do linear regression, it still might be messed up, right? Actually, no. The randomization also fixes the extrapolation problem. Which is kind of surprising, very interesting. So the idea is this: if you have, so here's an observational study. So here you can see the pink points are kind of skewed to the right, and we're missing a lot up here, and the gray are skewed to the left, and we're missing a lot down here. How is this different in a randomized trial? In a randomized trial, since the treatment is given randomly, you're not going to get this confounding effect where the older people are getting the drug more often than the younger people. You're going to have old people getting the drug. You're going to have young people getting the drug. You're going to have young people not treated. You're going to have young people treated. And so these dark gray points are spread evenly among X, and same with the pink. They're spread evenly. And so what we get there is if we do linear regression, whereas over here the linear regression is going to look something like that, right? And so you're going to underestimate the average treatment effect. If you do linear regression over here, it might look something more like this, okay? And the average difference here is actually very reflective of the average difference between these counterfactuals, right? Which you can't measure, right? You don't see these empty points. I'm just drawing them here, a couple of them, so you can see that the scale is right. So because it's not extrapolating, it's actually doing a good job. You could show this all mathematically as well, algebraically, but I think the picture maybe gives you a better intuition as to why the randomization gives you no bias, even if it's not a well-specified model. So it's a special case, however. It does justify why in a randomized trial you can just do linear regression, turn your brain off, and not really worry about it. You can still do better. We'll talk more next week about how you can do better than that, even in a randomized trial. But it's kind of a nice and surprising fact that people randomize primarily so that you can solve this identification problem. But then it also helps you in the estimation step. Very cool. All right, that's it for this part.